You're lecturing first.
Yes. Okay.
I was trying to understand what it means for U and H to be state functions, and I trying to understand it from like special like algebra. So if I wanted to like manipulate the equation delta U equals delta H minus P delta Z, I can really just do that, right? Because
Yeah, you could do it. You could see it's a state function in a lot of different ways. Tell me all the ways you could see that delta U is a state function. Delta U is a state function. Let me ask you, is temperature a state function? Then you ask delta T. Does delta T only depend on the initial and the final temperature, not how the temperature was cycled? So for example, if I start off at room temperature and I go up to 1,000 degrees C and then drop back down to room temperature, delta T is 0. But what if I only went up 500 degrees C? So I start at room temperature, go up to 500 degrees C, and then drop back down to room temperature. What's delta T? 0. So delta T is a state function. It doesn't depend on how you do it. It just depends on your initial temperature and your... And the same thing, any state function only depends on your initial and your final, not how it was done. This is why we could say metabolism of glucose and burning glucose is the same energy. We could say it's the same energy because the starting material and the ending is the same, right? We start off with glucose, we end up with CO2 and water. We burn it, it's the same thing. Either metabolize it, burn it, you're going to end up with the same stuff, which means you're going to get the same exact amount of energy. And so that's what it means to be a state function. It doesn't matter how you burn it. You can burn it in your body, or you can burn it in a fire. It doesn't matter.
how are Q, V, and Q?
Well, did you guys reviewed all that?
Yes.
Why isn't Q a state function?
Depends on which.
It depends on the quantity.
For example, if I have a delta T of 0 and I heat it to 1,000 and drop it back down to the room temperature, 1,000 degrees C, drop it back down, the amount of heat I have to input in there is it the same amount of heat that I have to input in, let's say, 500 degrees? No, the amounts of heat are quite a bit less. Right? And so heat is not a, yeah, because it varies. So. W? Path-dependent function. Spent a lot of time talking about the path-dependent versus using the example. What example did I use to talk about heat as a path-dependent function? It wasn't the slide. The slide I used, yeah. I used the slide to talk. That was heat and work, yeah. You get different amounts of heat depending on, but delta E is the same. It's a state function. That's good. So it was the slide. But there's one other thing I did, similar to this, talking about cars, methane combustion, right? Methane's used in CNG vehicles, which is different than a methane fuel cell vehicle. You know? Fuel cell is going to give you the least amount of heat, the most amount of work, actually. Whereas just a steam engine, does anybody drive steam engine cars? No, so if you had the methane burner and in the middle of your car you had a tank of water, and this tank of water you just boil to generate steam to drive a turbine to power you down the road, is that very... No, it's not very efficient. And so, but it's going to produce, burning the methane is going to produce a lot of heat, for sure. So we talked about that. And so the slide is good, though. Think about the slide in terms of heat and work. Okay, what else in your review of Chapter 7, you know, delta U and delta H, what other things? Was it clear to you? Is it clear to you? If it's clear to you, that's good. You know, that's where you want to be at this point. If there are holes, then you need to get those cleared up either by reading the book or reading other books or looking for videos, maybe a YouTube video or something, or, you know, Khan Academy, or, you know, asking.
We have longer office hours next week.
Yeah, usually I just stay for as long as people want. Unless I have some meeting or something to go to.
Or can you give us a time on like Piazza when you'll be on?
Okay, yeah, we could do that. Piazza time. When would be a good Piazza time? After you've had time to review and then see where all your questions are, what doesn't.
Like midnight to 3 a.m.
Midnight to 3 a.m. The weekend. So, how about Saturday or Sunday? What? Sunday. All right. Sunday at
Noon.
Sunday at noon. It's
That's later.
5
Like
p.m.
6
Yeah.
o'clock.
Sunday evening.
Sunday evening.
Yeah.
Let's do it like maybe 8 p.m. Sunday. How about that? Does 8 p.m. Sunday work?
That's late.
That's a little late, huh?
6 p.m.
Yeah.
Till midnight.
6 p.m. Sunday.
For how long?
Do you have Skype?
I don't have Skype. I do. I set up an account a long time ago, but I don't. Never used it. I don't know how to use it. So I gave up. I have FaceTime. Much easier.
Yeah.
All right, we could do Piazza. How about Piazza? We'll just do it like a chat session. You know, Sunday.
What time?
You said 6 p.m. on Sunday.
Yes. To what time?
2 o'clock. 2 to 6.
That's late.
No, it's too early. Too early. 2 o'clock. It's a very good day.
Oh, we could do. Let's see, Sunday. You want to do Sunday morning?
No, yes, that would be
Yes.
perfect. Too
We
early.
have to wait till Sunday evening so you have accumulated
Yeah,
questions.
so you have time to study. That's what you have Saturday for.
Really? You're just gonna
Really?
start Saturday, that's it?
That's not enough time.
We could do 2 sessions. I could do a Sunday session from
10 to 2. What if it
well, just it'll be 1 hour, 10 to 11.
Should you be like Dr. Ultimate and open up a lab and come?
Yeah.
Please, we'll buy lunch.
Yeah.
We'll bring donuts and stuff.
Krispy Kreme. I have a Krispy Kreme card. You buy
Here
it.
it
It's okay.
Please.
What kind of session would this be?
Like review
Yes, a review, questions.
of everything, all the
Everything.
calculations.
We can do it
We
now.
could do
It's
that.
probably.
We could do that on Monday. Let's see.
Tuesday? Tuesday's a holiday.
Tuesday.
Tuesday's a holiday.
Yeah. Yeah. Eat rest now. Get away from us.
Well, we could right now. Let's do this. This your question you went through. What doesn't make sense to you with delta U and delta H?
Too early. Like,
Is it
we're
too
gonna
early?
use the weekend to study and then we're gonna have questions at the end of the weekend.
Yeah, you're right. It is too early, I think. So we'll do that. But now's the time to get started and write down, the things that you don't understand, and then try to find the answer to those yourself. And if you can't, then
Or Monday evening would be good too. Like
Okay.
After class.
Monday we could do it after class. I have to normally have my office, but I have to go to another meeting on Monday right after class, which is going to go for an hour.
Can you come back?
Yeah.
Yeah, I can come back. So I'll probably be gone for
Oh, maybe we have class, then we can't do
to leave one of the rooms open, so we're just...
No, you could leave we can leave the room open. Except is there a class after ours?
I don't think so. I think there's a class at 6.
6. We could go in the computer lab, but if there's no class there, then just stay in the room. You could figure it out. Then we could have a review session if you want. Okay.
So the test will be half of 7, 8, and 9.
All of 7.
All of 7.
Yeah.
And the other
Some of
6.
6.
Some of 6, 8, and 9.
Oh, no 10?
No 10.
Oh, really?
No 10.
That's good. Yeah, it's chapter 2.
10 and 11 are kind of sister chapters. And so 10, 11 are Lewis structures and geometry and orbitals.
Oh, so this test is not going to have a bonding and loose structures?
Yeah, no Lewis structures on this test.
That's cool.
So we're doing 9 today.
Yeah. We're going to start 9. Actually,
Let's start.
but we haven't finished 8. So we're going to finish 8.
Okay, I have a question.
Uh-huh.
Heisenberg uncertainty. It sounds easy, but actually I don't get it. Like when you know the position of when you're precise in the position, that's mean your chance of knowing the momentum is less. I understand that, but I don't get it. Like,
Yeah,
how it
okay.
works.
Well,
I read the book and it doesn't make sense for me.
all right. The way you would imagine the Heisenberg uncertainty principle is something like this. Let's say if you saw a bird flying, right? If you saw a bird flying, you could just see it and then kind of pinpoint where it is. You can kind of track it and see where it's moving. But let's say if you were blind and you're trying to track the bird moving. And how do you do that? If you're blind, you would probably throw, little pebbles at the bird or something. And then you would listen for a sound, little pebbles at the bird. But would you throw a big rock at the bird? Because if you threw a big rock, do you think it's going to continue flying the normal path it was flying? Well, that's the problem with electrons. Can you see electrons with your eyes and just kind of watch where it's moving? No. And so how do you probe it? How do you probe the electron? Well, you're probing the electron with big rocks because you're throwing photons at the electron. But the problem is when the photon hits the electron, all of a sudden the electron was flying like this, maybe, let's say. It's flying like this, but you hit it with a big rock. Do you think it's still going to be flying like... No, it's like the bird. You throw a big rock. And so what we did was we pinpointed... Oh, I heard the noise there. We pinpointed where the bird is, but now I'm going to try to throw another rock to see which way it's moving, right? And so it was originally moving here, and then boom, now it's moving there, but originally it was going to move here, and you're throwing more rocks, big rocks, to find out where the bird is and where it's moving. It's impossible, right? And so that's the problem with the electron. The electron is like a little bird, and the photons you're hitting it with are like rocks. And so it makes it very difficult to pinpoint both the direction and its position. Something like that. Maybe that's not the perfect analogy for that, but another way of thinking about this is, and this is what people say, is that the photon perturbs the electron, and so that's like the big rock analogy. But every time you try to observe the electron, you upset it, you move it, and so something like that. The book uses the thing about the film. Did you read that about the film?
Mhm.
Yeah. Like if you were at an intersection, a really busy intersection, and you tried to record this with a camera, a still camera, not a video camera, but a still camera. What you could do in photography is you could, this is like when it's dark outside, you get ghost images because the exposure time is very long. So you could set a long exposure and watch the cars move and see what direction they're moving. But everything's a ghost image. And so you aren't pinpointed. There's no pinpointed position there. I guess over time there is. But the other is if you take a sharp photo and freeze everything in its place. Then you know the precise position of everything, but you don't know what direction everything's moving. And so that's the other analogy that's used to understand the Heisenberg uncertainty principle. So those two things. But the main thing you need to know about the Heisenberg uncertainty principle is not necessarily the origin of it, but what it means for us. What it means for us is the orbital, we know the energy of the electron, but we don't know the position. You know, the position is not totally random. The position is given by some probability, so have a general idea of the position, but not the precise one.
What did you call the crisp image? The photo that was like the one you.
Then you know the position. You know the position, but you don't know its direction or energy, how fast it's moving. You know, how fast is that car moving? How fast is this car moving? You know, because everything's frozen. And so you lose the velocity information. That's what they say. Velocity is what direction and how fast. Okay, other questions? Well, we got a projector working in here, so let me. So remind me on Monday. Oh, wait. After class is no problem on Monday. Yeah, right after class, it's right after the morning class I have a meeting. And so this class I can stay. So we could have a review session then.
For how long?
Actually, on Monday, as long as you want. I'll
If
just.
some of us have class after 2 at 6 o'clock. So can we do another time? Because we only have like an hour.
For those that don't have time, it's like 3 hours. It's, you know, page 325.
Can you still do the piazza session?
A piazza session on when? Sunday?
Anytime.
Anytime?
As long as you're behind the other side.
Yeah, we could do a piazza session. Just piazza session on Sunday evening?
Yes.
All right. Piazza session Sunday evening? What time? 9? Sunday night? 9 p.m.?
Earlier.
I thought you said Sunday morning.
You're the only person who said that.
Sunday morning. Seriously, you just said that.
How many people would like Sunday morning, 10 to 11?
It's Sunday morning.
People have church.
How about Sunday night? All right.
I say either Sunday night or Monday night.
Okay, Monday night. Is that
We can
better?
make it easy and post the questions beforehand too, and then we can just
Can you
compare.
say it's about a morning?
It's only you.
No, but they won't.
Majority.
But you still have your.
Yeah, you post your question
Yeah, why
between.
doesn't it have to be
If
the
you have
same time?
questions between 10 and 11, I'll have the computer on between 10 and 11, so
Okay.
it's okay. Just post it and I'll see. And so 10 to 11 on Monday, and then Sunday night. What time?
6 till 9.
6 till 9.
6 to midnight?
Ah,
$6 to $9 sounds good.
6 to 9 is.
Unless you have.
What if we just
How is it
post?
gonna eat there?
What if we just post our questions throughout the
Yeah.
weekend and you
Yeah.
answer them on Sunday night whenever?
All right.
Yeah.
Yeah. All right. I'll answer them Sunday. Post your questions and then I'll answer. Or if you can answer the questions, that would be good too. Somebody else's question, and then I'll log on Sunday night, 6 or so. Okay. See.
And then we get FaceTime on Monday.
No, you could. I mean, we'll have a real session.
Yeah, that's what I mean.
I mean,
like,
real session.
We'll be here.
I want to sign out.
What weekend? Oh, Indonesian said he's keeping the same max rate too. The same week as it's holidays.
I know, that's what I said. I knew it was Leo.
So where did we leave off talking?
You didn't talk about much yesterday.
Yeah.
You lectured us more. So you did the 300.
All right, we talked about why these are the same energy, right? The 2s and the 2p, even though they're different shapes, they're the same energy because, yeah, they're degenerate, but why are they degenerate? Yes. Yeah. So they have the same effective radius or the same effective distance from the nucleus, n equals 2. And we said the same thing for these, the 3s, the 3p, and the 3d. All those orbitals are going to be the same energy because, yeah, they're going to have the same effective distance, right? The same effective distance, which means that they're going to result in the same energy, even though they have different shapes. So the different shapes are going to show you a different okay, here's the 3s, the 3p, and the 3d. Do you know what these graphs are? These are the RPDs. RPD stands for radial probability distribution. And what does RPD tell us? Yeah, the closest, which is what? The, what do we call that? The most probable distances. These are the most probable distances from the nucleus. And so if I look at the peak here, at the top of the peak, this should be the most probable distance from the nucleus, right? Right at the top of the peak, so around here, 13. And so a 3s orbital here is going to be about 13. And then I look at a 3p orbital. 3p orbital is more like 12. And the 3d orbital is more like 9. And so I'm looking at this, I'm going, the 3d electron most probably is going to be closer to the nucleus than the 3s. And so the question I'm going to ask is, why isn't this lower in energy? Because the closer the electron gets to the nucleus, the lower in energy it should become, because the further and further out you pull the electron, the higher in energy it should be.
I thought we were looking at the y-axis as though that was getting closer to.
No, 0 is the nucleus here.
Okay.
The y-axis is this probability thing. The y-axis could be the number of dots captured in the ring, if you want. This ring here captured, let's say, 1,000 dots. This ring here captured 800 dots. That kind of thing. And so what did I say about that? Yes, the 3d electron has a most probable distance that's closer to the nucleus, but the distribution in three-dimensional space.
It allows you to gather more of the dots. The volume being, even though it's a wider circle, you're gathering more of the dots, so it ends up. So even though it's not concentrated around the nucleus, you're still getting.
Did I show you the origin of these? I might have skipped that. I forgot how far. But what you're talking about is this. you talking about this?
Yeah.
Yeah, okay. Did I do this? The 1s orbital?
Yeah.
Okay. And so you just see what's plotting on the y-axis is how many dots are in the ring. And so the more dots, the higher up you're going to be on the y-axis. And it turns out, if you look at the concentration of the concentration of the dots is highest right at the nucleus. But right at the nucleus, we don't have the most dots. Why? So the volume is small. And so we plot this out, and if we plot that out, this is what this one looks like. This is small. Should I just have the fingers? On the bottom. All right, so this is what that looks like here, right? And so we can see the most probable distance. The most probable distance for a hydrogen 1s electron turns out to be 53 picometers or so. And then we have the 2s. We look at the 2s, it looks like around 6. Do you see that? The 2p looks around 4, maybe, a little bit below 4. And so which one is closer to the nucleus, it looks like? The 2s or the 2p? Looks like the 2p. If the electron in the 2p orbital is closer to the nucleus, shouldn't it be more stable? And so shouldn't the 2p orbital be lower in energy than the 2s? No, the 2p orbital is the same energy as the 2s. And so the question is, why are they the same energy? Have you answered the question? You've answered it because they both have the same effective distance. But when I look at the distance, I see the distances are different here. Yeah, this distance is not the effective distance. This distance is the
Highest probability.
yeah, highest probability. But what is the effective distance then? What's the difference between this and the effective distance?
To normalize.
Yes, you have to normalize it. You normalize it over 3 dimensions because remember, this is what we call a iso or anisotropic. A 2s, is it isotropic or anisotropic? I heard 2 different answers. Iso. Iso means same, right? In every direction. And so this is isotropic, but this is not isotropic. A 2p has one lobe on going, let's say, on this axis, another lobe on this axis, and nothing around here. And so a 2p orbital is anisotropic. So what we have to do is we have to spread out all those dots to make a fair comparison over 3 dimensions and make it isotropic. And so if we have this electron, which is now trapped, right? Did I draw a little figure showing the 2p? Yes, I did. With the circle and the dumbbell. Yeah, this is just review. I'm just, you know, you guys should be reviewing this yourself, you know, after every class. And then seeing what doesn't make sense. And then the next day, make sure to ask. And so we started the whole, you know, I spent a lot of the time just to answer one question. And that one question was brought up at the beginning. That one question was, why are these 2 orbitals the same energy? And so do you have the answer? Yes. And do you understand why these are different and effective different distance is the same? Yes, okay, then you're good. That's what you want to know. We talked about that. You want to understand that for the test, and you're good. Okay. Well, we can carry this on. You see the 3S? It's like this, the 3P and the 3D. And even though the 3D has the most probable distance closer to the nucleus, it's the same situation, because if we normalize it over all 3 dimensions and make it isotropic, then all 3 of these should normalize to the same effective distance, which gives the same energy. And in fact, what is the effective distance for an n equals 3 electron in a hydrogen atom? It's A naught over, or no, n squared times A naught. You guys remember this equation? Or equals n squared times 0.53 angstroms. Well, n is 3, so it's 9. 9 times 0.5 is 4.5, roughly. 4.5 angstroms would be the effective distance. That corresponds to the 3rd Bohr orbit. The 3rd Bohr orbit. This is the 1st orbit. The 2nd orbit is 4 times. The 3rd orbit is
9 times.
9 times. This is the effective distance for the nucleus. But does the electron stay there? No, electrons all over the place. Oh, here's the 53 picometers, 0.53 angstroms here. This is what we call A9.
What thing is that?
308. We know this model's wrong, though. Right? This model's wrong. All right, so to answer that question, so for 1 electron species,
Professor, angstrom is a unit just like picometers.
no.
So when I do the calculation,
Well, yes and no. Angstroms is like picometer because they're both lengths. But pico is just a generic term meaning 10 to the minus 12. So you could have picoliters, picometers, pico whatever. But angstrom only has 1 unit, and that is length. And so you'll never have angstroms used for volume. You'll never have angstroms used for energy. You'll only have angstroms used for light, whereas pico could be used for joules, picojoules, picoliters, pico whatever. And so that's how they're different.
This is where I'm confused. Why the lithium, for example, why that is not the same energy level?
Yeah, that's the next question.
Oh.
So we understand why these are the same energy levels, right? And these are the same energy levels. So the next question is, why are these not? And so for 1 electron species, this is what we have. And the difference between 1 electron species, if we modify this for other 1 electron species, then we'll see that, yeah, the energy is always equal to n, but it's going to have this z squared. So it's going to be minus z squared r sub h over n squared. And so we modify the energies. Let's say if we looked at another 1 electron species like helium plus, what's the difference between a hydrogen and a helium plus? Well, both of them have 1 electron, and so they're the same. They have different amounts of protons. Helium would have 2 protons, whereas hydrogen would have 1. And so what impact, did I ask you this? What impact does that make? Yes. All right, with one proton, you're an electron out here, and you're going to be attracted to the nucleus. And so the one proton keeps the electron from traveling too far away, right? It'd be too high of energy to escape. And so the proton is always there. But what if you have two protons in there? If you have two protons, then that leash is a lot stronger, and that means the electrons are going to be held much more closer. If the electrons are held much more closer, what does that do to the size of the orbital? Okay, so 1s orbital on a species like helium plus is much smaller. And what does that do to the energy? Now the effective distance is actually much shorter, decreased. So the effective distance is much closer, meaning it's lower in energy or higher in energy? Lower in energy. And so a 1s orbital on a species like helium plus is going to be lower in energy. And so this is why we can see this trend here. The first trend we notice is that what happened to the 1s energy? Shouldn't the 1s energy be the same for lithium? No, it shouldn't. The 1s energy is going to be lower because lithium has how many protons? 3 protons. And those 3 protons are going to pull in that 1s electron or 1s electrons close to the nucleus, making the energy lower. And so the orbital here is much bigger than the orbital here. This orbital is much smaller and lower in energy. That's no problem. The same thing is going to happen with the 2, right? The 2s electrons are going to be pulling closer. Therefore, the 2s orbital here is going to be smaller, and the electron's going to be closer, and therefore lower in energy.
Did you say earlier that the further the electron, the larger the energy?
Yes. And so
here you said if it's closer. Wait, what did I say? No,
You have it correct.
no. Didn't you say that if the electron is further, the energy is lower?
no. No.
Because if it's the
No.
if infinite distance, then it's 0. The energy is 0. No.
Oh, yes. Yes, the energy is 0, right? But what is this energy we're talking about? This is crazy because this is 2.179 times 10 to the minus 18 joules. It's negative. And so when I say lower in energy, the highest energy here is 0. And so 0 joules would be high energy. And negative 2.179 times 10 to the minus 18 joules would be low energy. It's because of this. It's arbitrary what they pick as 0. They just thought, you know, the easiest reference point to call 0 is when the electron and the proton are infinitely far away. We'll call that 0. And then as the electron approaches, then things become more stable. And so they could have called this 0 down here, but they didn't. You know, they decided, whoever did this decided to call the top 0 rather than the bottom. We're so used to doing the bottom as 0, right? But, you know, it's totally arbitrary because this 0 doesn't match up with anything in lithium. You know, if we call this 0.
But why isn't that larger energy than 0? I mean, it's negative, but there is no negative joule. I mean, it's just
there is no
call it that.
Right. And so this one, if we call this 0 joules, then the top would be positive 2.179 times 10 to the minus 18 joules, right? Okay, so now if we use this scale, then what happened to the energy? It dropped. The same thing here, the energy dropped. And so it's getting lower in energy. It's the same thing, you know, like if people are walking on a narrow piece of board and the narrow piece of board is on a sidewalk, it's easy. Most people can balance and walk across this board, right? But if all of a sudden you put this board between 2 high-rise buildings and then try to walk across it, then it becomes hard because all of a sudden you're thinking about energy, right? This is going to be high energy scenario versus low energy, low risk scenario. So the further away you get from the ground, the higher the energy. The further away you get from the nucleus, the higher the energy becomes. And so the other way of thinking about this is the electron is being held, it's being pulled into the nucleus. And so if you came along and tried to take that electron away, you're going to get into a tug of war with the nucleus. The nucleus is pulling on the electron, you're pulling on the electron, you're trying to pull the electron away from the nucleus. The nucleus is trying to pull the electron in towards it. You know, and so the electron, the further it gets out from the nucleus, the higher energy it becomes, and the less stable it becomes, because it wants to go towards the nucleus. But one thing, you know, this is okay, the 2p drops in energy, but what's going on here and here? And so the next question we need to answer, well, you can see what's happening here. The orbitals are just getting smaller. They're getting closer to the nucleus here. But this pattern repeats here. And then this is a weird thing here that happens as well. And so we'll talk about these things in a minute. And so the question is, why are these not the same energy? You know, we just got done spending a lot of time talking about why those are the same energy. And did something change? So for example, did the effective distance change? What do you think? I don't know. Maybe.
I thought you were saying that those two were the same energy.
Maybe. I did.
Wait, now you're saying they're not, or you're still saying? Are you asking them?
They are the same energy for hydrogen in one electron, but when we go to lithium, they are not. And so why is it, actually, it doesn't even have to be for lithium, for helium. Not helium plus, but just plain old helium. They're not the same energy.
Well, the extra proton changes the effective distance, right?
Yeah, the extra proton changes the effective distance, right? But does it change the effective distance for both of those?
Do you mean, does it change it in a different way?
In other words, doesn't the extra proton affect both the 2s and the 2p the same? I mean, for example, the extra proton, let's say the extra proton here are protons. This is +3. Now we got a +3 charge. And so are you telling me that the +3 charge for 2s is different than the +3 charge for 2p?
In that case, there are two electrons, one on the 2s and one on 2p?
No, no electrons right now. Just this is where their energy is. We could put one electron there. It doesn't matter. I could put one electron here, or I could just leave it empty and put one electron here. So I only got one electron, and I could put it in either one of these.
But you said if there's only one electron, then it would be equal, like on the left side.
Yes. If there's one electron, it would be equal. So let's go to helium. Helium has 2 electrons. We'll put them here. Now I'm at lithium. I have one more electron. Which one do I put it in? Into a 2s or a 2p? 2s, because 2s is lower in energy. Why is a 2s lower in energy than the 2p? Because is the +3 charge different for 2s than for 2p?
I thought it was just the rule you go to the lowest energy level first. And fill in the lowest first.
Yeah, you do fill in the lowest first, but why is this lower in energy than this? When I just got done saying that they're the same energy. Aren't they the same energy? For hydrogen atom, it doesn't matter. Same energy. But for lithium, it matters. They aren't the same energy. And so the question is, take a step back, and then what is the origin of this, what we call splitting of the degeneracy? They used to be degenerate, but now these two subshells are different energies. And so the question is, where did this splitting come from? Why are these no longer degenerate?
The other electron?
In other words, the 2s appears to be lower in energy, more stable than a 2p. 2p is higher in energy and less stable. And so why is that? And so the answer is the splitting comes from these two concepts, penetration and shielding. Penetration and shielding, because when we have multi-electrons, we have electrons down here, let's say. When we have a single electron, you know, if an electron were up here, then there's nothing between this electron and the nucleus. The nucleus is going to have +1 for hydrogen or +2 for helium plus or whatever. Now here, if we have one electron here, well, the nucleus is going to be +3, but now we have these 1s electrons between them. And so let's talk about penetration and shielding. And how that arises. So for a hydrogen atom, you know, a hydrogen atom normally has an electron here in the 1s. And the 1s could jump. Let's say the 1s jumps up to n equals 2. And then n equals 2, the electron might be in a 2s, like that, or an electron might be in a 2p, like this. It doesn't matter because these both have the same effective distance. They're both going to have the same interaction with the nucleus. So that doesn't matter. But the problem is for multi-electron. Multi-electron, there are other electrons interfering. And how do the other electrons interfere? Well, this is how the other electrons interfere. We look at this, you know, this is from 0 to 5. It peaks around here, let's say. What we have to do is we have to consider that this electron here is still there. And so what we have here is a 1s electron like this. And so we got this 1s electron in here. Yes. Now, if we put a 2s electron here, what we see is there's going to be some shielding, in other words, blocking of the nuclear charge. The nucleus is over here. And so let's do this as helium. So let's say there's +2 in the nucleus here. If there's +2 in the nucleus here, then is this electron, the red electron, going to see the full +2 charge? No, it's not, because what's happening is this purple electron is blocking some of the nuclear charge from this. And so it doesn't see the full effect of that nuclear charge. This +2 is called Z. The amount of nuclear charge that this electron experiences is diminished because of this electron here. And so what we see, the electron sees, is something called Z effective. Z effective is, you know, how much nuclear charge that electron experiences with this electron blocking it. Let me just do this really quick. For one electron species, there's no electron blocking it. Here. And so Z and Z effective are the same. But all of a sudden, for multi-electron, then we got to figure out some of these other electrons are going to block some of the nuclear charge from there. Well, that happens to this, whether the electron is in a 2s or a 2p, doesn't matter. This electron is going to see diminished nuclear charge that we call Z effective. And so these what we call inner electrons, the 1s for the outer electrons, the 2, these inner electrons are pretty good at blocking the nuclear charge from the outer electron. All right, but there's a difference. If you look at the RPDs, radial probability distributions, do you see the difference in shape of the RPDs? The 1s electron's blocking, and so it's going to try to block either the 2s or the 2p the same. And so let's say the 1s electron's blocking like this. We look at the shape of the RPD, and what we see is this. This electron might be able to sneak around the 1s electron over here. So if this electron pops in over here, then it gets very close to the nucleus. And if it's very close to the nucleus, what's going to happen to Z effective? Is it going to be as blocked? No. And so if the electron pops over into this lobe, then the Z effective it feels is much greater. Does that make sense? In other words, this electron is trying to block, but the electron can sneak around behind it and then make it to the nucleus. How about this electron? I'm going to try to sneak this electron around this electron here and get to the nucleus. Can this electron sneak close to the nucleus and get around this blocking electron? No, the reason is because there's very little probability of finding that electron near the nucleus based on its RPD. If you look at it, this is the probability. It's minuscule, the probability of this going around this electron, right? Whereas this electron, the probability is kind of big because look at this hump here. This hump is just probability that the electron is going to be this close to the nucleus. And so in this case, this electron can sneak in, at least into the same space or behind this purple electron to see more nuclear charge. And the more nuclear charge it sees, the higher the Z effective. And so let's break this down to like this. This is what we say. The 2s electron is more penetrating than the 2p electron. The 2p electron is less penetrating. If the 2s electron is more penetrating, then that means it's less shielded. Less shielded. More penetrating, less shielded means that Z effective is going to be bigger than this. This is less penetrating, more shielded. And therefore, Z effective is smaller. And the greater the Z effective, the more stable that electron is going to be. You know, because we need the positive and the negative. And so that's because of this 1s electron. And so this is the case for multi-electron species. For multi-electron species, we lose the degeneracy in the subshells. Does this make sense? All right, let's take a look at this. let's compare the 3s, the 3p, and the 3d. Which one is more penetrating? Is the 3d very penetrating? Can it get close to the nucleus? No. How about the 3p? Oh, that's pretty good. Look at this. The electron can sneak in here. The 1s and the 2s are around here. The 1s are going to try to block the nuclear charge here to about 5. So the 1s are about here. And then 2s and the 2p are around 5-ish. So those are going to be trying to block it. But it can sneak in. Do you see that? And get close to the nucleus. Is the probability. How about the 3s? Okay, look at the 3p and take a look here. Right there. You know, it has pretty decent probability it's close to the nucleus. This one's kind of far off. Do you see it kind of tails off there? The 3p gets close. It could be pretty close to the nucleus, right on the nucleus, right there. See that? How about the 3s? 3s is a much higher probability of being right next to the nucleus. That means any electrons trying to block it, it can sneak in and around, or at least sneak in and be level, the same, right? Because you're going to have the 1s here, the 2s, the 2p, all these electrons blocking it from where it normally is. You know, the electron's normally here, let's say, the most probable distance, and you have all these other electrons blocking it. But if that electron happens to move close, then it's going to be quite a bit more stable. And so we see that this is the most, what we call 3s would be the most penetrating or the most shielded? The most penetrating. 3d would be the least. 3s would be the least shielded. The 3d would be the most shielded. And in terms of energy, which one would be the lowest in energy? The 3s. And so the 3s is lower in energy than the 3p, which is lower in energy than the 3d. So it's going to go this way. And so we see we're going to lose that degeneracy that we once had, because the degeneracy is assuming that, you know, even though the effective distance is the same in all these, how much positive charge they see differs because of penetration and shielding. So we see that right here in this diagram. The 3s is the most penetrating, followed by the 3p, followed by the 3d. But something happens here. Take a look at what happens here. The 3s is the most penetrating, followed by the 3d, not 3d, 3p, followed by the 4s. And so it turns out the 4s is more penetrating than the 3d. And so this is going to result in different, what are these diagrams called?
Energy level diagram.
Energy level diagrams. So here we go. Technically, the orbital energy level diagram. And this is how you draw them, the orbital energy level diagrams. On the test, oftentimes I ask people to write out the orbital energy level diagram, and I always get, you know, some students do this, 1s2, 2s2. Is that an orbital energy level diagram?
No.
No, but maybe a fraction of students think so. No, it's not. Or they draw this, 1s, 2s, 2p. Is this an orbital energy level diagram? No. This, I mean, it's close because we're ordering these, but it doesn't show the gaps. The biggest gap is between 1s and 2s. And the gap between 2s and 2p, is that huge? No, it's a very small gap. And so the orbital energy level diagram tries to show you the relative energies on a vertical scale. And so some people write this, and, that's wrong. Well, you should know how to write two orbital energy level diagrams for the test. One is the single electron species. It's pretty easy. And the other is for multi-electron species, in which we have to factor in the penetrating. Now, writing the one for multi-electron, you can be helped by doing this. You know, how do you remember this ordering? I mean, how do I know if 4s is more penetrating than a 3d? Now, how did I know that? You memorize it. And fortunately, it's not that difficult to memorize because we set up this pyramid, and it follows a simple pattern, usually. The pattern is a diagonal pattern. So we go 1s, and that fills a shell. 2s, 2p, that fills another shell. 3s, 3p, 4s, 3d, 4p. That's another shell. And so it's kind of weird. Over here, it's easy. The first shell, the second shell, the third shell. Over here, it becomes a little messy. And so let's go ahead and draw the diagram. I'd like you to be able to do. So we'll put the 1s at the bottom. So here's my 1s, or psi 100. And then the 2s and the 2p's. And then the 3s and the 3p's. But the 3d's are they in the same shell? The 3d's seem kind of mixed up with the 4s. And so it goes like this. It goes 4s, and then, actually maybe I'll write it over here. 4s and then 3d. Followed by 4p. And in the next shell we have 5s, etc. And so we define the shell a little bit differently. Over here, the energy level and the shell are defined the same. And so the first shell consists of the first energy level, n equals 1. The second shell consists of n equals 2, third, n equals 3. Over here, it's a little bit different. The first shell is like this. And the shell of orbitals would just be a set of orbitals that are close in energy. And so here we have the second shell. It's okay. But the third shell is missing the 3Ds. So this is the third shell. And just consists of 3s and 3p. The fourth shell is missing the 4f's, but it includes the 3Ds. And so the fourth shell would be 4s, 3d, 4p in that order. Fourth shell. And it turns out the 4f's, the 4Ds and the 4f's are actually in the next shells above. So remember the law of subshells? There are n subshells for every given n. And so that was over here. Very easy. In n equals 3, we had 3 subshells. 3s, 3p, 3d. Well, the same thing over here. n equals 3, we have 3 subshells, 3s, 3p, 3d, but it just so happens the 3ds are now going to be in the next shell, not in the same shell. And so the subshells, where those subshells are located is mixed up when we go multi-electron. And so what we'll do is we'll just call it a shell, the 4th shell. First shell, second shell, that kind of thing. And so let me just, do you guys want to take a break or just go on for a little bit more? Break? All right, let's take a break.